So now let us watch a video that can help us to understand more.
Couse Knackers!
Hey guys, welcome back to Couse Knackers. In this video, we're going to talk about three important concepts: valence bond theory, atomic orbitals, and sp3, sp2, and sp hybridization. So if you're ready, let's get right to it. Valence bond theory provides a very simple and useful way to understand how atoms are bonded together. For example, take a look at these two hydrogens coming together and sharing of these two electrons, one from each hydrogen, in forming a covalent bond. In valence bond theories, it's thought that electrons are localized in a region around a specific atom. In order for us to understand this bonding behavior and even more complex bonding behavior, we need to review the basics of orbitals. So let's take a look at them now. Atomic orbitals are areas of high probability of finding electrons. At every energy level, there is a 1s orbital in the shape of a sphere right over here. There are p orbitals. There are three p orbitals, the px, py, and pz. They look like dumbbells. And then finally, there are d orbitals. There are 5 d orbitals. Here are the shape of the d orbitals. Some would describe them as cloverleaf. Other people see them as 2 dumbbells attached in the middle. And then there are also f orbitals, 7 of them. But in this course, we won't be concerned with d and f orbitals. We'll primarily be concerned with s and p orbitals. Valence bond theory allows us to see how these two hydrogens share a covalent bond. Each hydrogen is under group 1, so it's 1s1, 1s1, allowing for the two electrons to come close together because they're attracted by the opposite nucleus, forming a covalent bond. This is very simple and straightforward. But what about more complex example, such as the following? CH4, this double bond, and this triple bond. How does valence bond theory explain the bonding behavior among these structures? Let's take a look at hybrid orbitals in order for us to explain this. In order for us to explain this, we have to take a look at a concept called hybridization. If you take any orbital, in this case an s orbital, and a p orbital, and you put them together, so you fuse them together, and you create what we call hybrid orbitals. So notice by combining an s and a p orbital, we get this sp orbital right over here. This is what we call a hybrid atomic orbital. Now going to look at the concept of hybridization. Let's see how sp3 hybridized carbons come together. So if you recall that carbon has 6 electrons, if we write the electronic configuration, it's 1s2, 2s2, and then 2p2. We're concerned with the valence electrons of carbon, so notice carbon has 4 valence electrons. Let's take a look at how we can fill this energy diagram. Here's the 2s, and then we can write in the 2p's. Remember that carbon has 3 2p orbitals, 2px, 2py, and 2pz. Initially, we fill the electrons from the ground state. We start out with 2 electrons in the 2s, and then we're going to add on 2 electrons in the 2p. In order for carbon to participate in sp3 hybridization, what it has to do is it first has to promote 1 electron from its 2s into its 2p orbital. So we're going to take 1 electron away and promote that electron into the 2p orbital. Now what happens next is the 2s orbital will go and it will fuse or hybridize with all 2p orbitals. When it fuses and hybridizes with all 2p orbitals, what do we get back? What we get is an s orbital, and then we fused it with the p orbitals, but there's 3 of them, so we get sp3 hybridized orbitals. So I'm going to write all of these as sp3, so we're going to fill them out. So these are all sp3 hybridized orbital, and they're more stable. So the sp3 hybridized orbital is more stable than the individual 2s or the 2p's. We call this degenerate because they're on the same energy level. Now let's fill in the electrons. So we have 4 electrons. So 1 electron goes into here, 1 electron goes into here, and then the 2 green electrons go into there because we have 4 electrons. These are the sp3 hybridized orbital that's represented by this schematic diagram. Now if hydrogen came along, hydrogen in forming a bond would supply an additional electron. So if we had 4 hydrogens right over here, each one of these hydrogens would participate in this sp3 hybridized covalent bond. Now the last point to make over here is that notice that in these sp3 hybridized orbital, it's 25% character s because there's only a 1s orbital, and then there are 3 p's, so it is 75% p character. Here's just another schematic representation of our sp3 hybridized carbon. Remember that each one of these bonds share 2 electrons. One of the electrons came from the sp3 hybridized orbital. So I'm just going to draw that electron right here, make it a little bit more clear. Okay. And then the second electron came from the hydrogen, sharing that second black electron. And that's how we explain covalent bond using sp3 hybridization. Now carbon takes on other hybridization, such as this sp2 hybridized carbon right over here. sp2 hybridized carbons are seen in double bonds. They're formed by the overlap of p orbitals, which we call this a pi bond. Now how does that pi bond occur? In order to answer that, let's take a look at our energy diagram again. Here's an energy diagram for sp2 hybridization. What we first do is we promote this electron into this 2p orbital. So I'm going to change that. I'm going to take away this electron right here, and we're going to promote it into this 2p orbital. What's going to happen in sp2 is we're going to take the 2s orbital, and we will fuse it or hybridize it with 2 of the 2p orbitals. So we're going to take that and we're going to hybridize it with these 2 p orbital, 1, 2. In doing so, what we end up creating is an S with a P, but there are 2 p orbitals, so we call it an sp2 orbital. So these are also both sp2 orbital. So I'm just going to draw them in. We have 3 sp2 orbital, and notice what we have left is an unhybridized p orbital. So right over here, so I'm going to write that. Okay. So here's an unhybridized 2p orbital. So we put in all the electrons, 1, 2, 3, and then the unhybridized p orbital is right here. Now this unhybridized p orbital, in forming a double bond, it goes and it shares that electron with another carbon's unhybridized p orbital. So I'm going to draw in this additional electron. And the sharing of these 2 unhybridized p orbital, we call that a pi bond. Okay, so a pi bond is really a double bond that's formed by the sharing of 2 unhybridized p orbital. So that's what an sp2 hybridization energy diagram looks like. So if we go back to this schematic diagram right over here, C2H4, you can see that the double bond was formed by a pi bond, the sharing of electrons between 2 unhybridized p orbital. So if we draw it in on this side right over here, this is the schematic diagram that we should see, the sharing of electrons between 2 unhybridized p orbital in forming this double bond. Now you know how sp2 hybridization works. Let's take a look at what sp hybridization is. Here's a diagram of C2H2, which takes on sp hybridized orbital. It's a triple bond. In forming the triple bond, you'll notice that you have a pi bond right over here, another pi bond, and then the middle carbon is actually a sigma bond. So how does this bonding behavior occur? How did I develop the 2 pi bond? Let's take a look at our energy diagram in order to explain this. Here's the energy diagram for sp hybridization. So we first promote this electron, as we did with the previous 2 examples. I'm going to draw on that single electron. Now what happens is that this 2s orbital hybridizes with only one of the 2p orbitals. So let's say it hybridizes with only this one right over here. I'm just going to shade this in. These two hybridize together. And what we get back is we get an sp hybridized orbital. There are these two other p orbitals that are remaining that are unhybridized. So I'm going to shade them in pink so that we can see them right here. We're going to draw them in. These are the two unhybridized p orbitals right there. We're going to place in electrons. Here's a red one, and then here's a green one, okay? And then we're going to place in the two remaining unhybridized p orbital. So remember, it's these two orbitals right over here, okay? With the unhybridized p orbital, these are the p orbitals that are used to form a triple bond. So I'm first going to take this electron right over here. I'm going to put it in this p orbital, okay? And then I will take this electron right over here, this red one, and then I will put that into this p orbital. So these two unhybridized 2p red and green electrons will go and share these electrons with another carbon's unhybridized p electron, represented by these two blue electrons that I'm drawing in. Then the green electron and the blue electron will form the first pi bond, and then they will form this second pi bond. So this is how a triple bond is formed in sp hybridization. So remember that this double bond is formed by the sharing of these two p orbitals. So I'm going to put in the electrons. So remember, recall that we're going to put in these two electrons, one electron up, one electron down. So when it shares these two electrons, we form the first pi bond. The second pi bond comes from, so I'm just going to change this color right over here so that it's a bit more clear. The second pi bond comes from this red one. So notice right here, I'm just going to highlight it. This red one that's perpendicular. So I'm going to put in those electrons. So here's one electron pointing up, here's an electron pointing down. And it's from the overlap of these two electrons that we form a second pi bond. And this second pi bond right over here. So this is how sp hybridization works. Hopefully you've gotten a better understanding of how sp3, sp2, and sp hybridization works. Hopefully this video gave you a good understanding about hybridization.